Today we are going to learn about some statements and postulates, theorems, definitions that we can use as we begin writing our proofs on segment and segment relationships. The first three properties that we're going to work with are very similar to the ones that we have previously reviewed from algebra and the properties of equality. These are actually the same properties as they apply to congruence instead of equality. So reflexive property stays the same, only we're changing the congruent symbol in the middle. So these two segments are congruent to each other. They're the same segment, so segments are congruent to themselves. With the symmetric property of congruence, we have if you know that two segments are congruent, you can switch the order and say that CD is congruent to AB. And then the transitive property says that if you have AB congruent to CD and then segment CD congruent to EF, you can go straight to the conclusion that segment AB is congruent to segment EF. So these, just make sure when you use these in a proof that you use the term congruent. So it's the reflexive congruent property, symmetric property of congruence, not just reflexive or just symmetric. Okay. We need to distinguish it from the property of equality. The second thing that you can use is definitions. So we are formally here defining the definition of segment congruence. And what it means, if two segments are congruent, that happens if and only if their lengths are equal. Okay, so segments are congruent if and only if their lengths are equal. This is really important, and we'll use this often because when we want to do addition and subtraction with segments, in order to do that, you have to have equality. We cannot do addition and subtraction with congruence. So this is a tool that we use to convert back and forth between congruence and equality. Right? So this is very useful. You will need to use it a lot. Okay, notation is extremely important here. So notice on the congruence statement, we have to use the segment symbols. Excuse me. We have to use the segment symbols on top of those segment names. Whereas when we're talking equality, we don't need the segment symbols. Okay, that notation is really important. And here's an example of a postulate, the segment addition postulate, that allows us to deconstruct segments into their smaller parts. So anytime you have a segment and you have a point that's in between two other points, you can create this statement where you are decomposing the larger segment into its two smaller parts. So I'm talking about the length of AB is the sum of AC to CB. And that's true anytime you have any point that's in between A and B. So I could have other points on that line segment that it would be true for. Okay, so I could write similar statements for a point like this. That might be the midpoint, or a point that's way over here. Okay, it doesn't matter where the point is. You can always write a statement like this. So let's go ahead and walk through a very common style of proof. You're going to see it a lot through your proofwriting time. So I want to first just break down what the question is asking. So it asks us to prove that if we're given that AC is congruent to BD, then our job is to prove that AB is congruent to CD. So sometimes it's helpful if you look at the picture or can draw one. So here's segment AC and here's segment BD, and they want me to show or prove that these two smaller segments, AB and CD, out here on the edges are congruent. The thing that I notice when I look at this picture is that there's this section here, BC, that those two larger segments share, and they overlap there. So when we start to hypothesize, how are we going to prove this? I start to think of taking out that overlap so that I'm left with those two small side pieces. So that's exactly what I'm going to do in my proof. So keep in mind, we're going to look at structure here for a second. I am starting my proof with the given information. Remember, your hypothesis is your givens. Okay, so that's going to go as your very first statement, should always be what you're given. Okay, and your justification for that is just it's given. We're assuming that is true because that's the given statement. And then notice that I'm ending my proof with the same statement I've been asked to conclude with. Okay, that is my ending statement in my proof. And then I have to fill in the rest on my own. Okay, so I propose the idea that we're going to subtract out what this overlap entails. So that means that I want to do addition and subtraction with my segments. So if I'm given it as a congruent statement, we just discussed we need to be able to convert to an equal sign so that we can do some addition and subtraction. So that's my first step. My first step is to make that conversion. So I said, okay, let's just convert. So I converted from segment symbols and a congruent symbol to no segment symbols with an equal sign. And my justification for that is I use the definition of congruent segments. Well, I know some things about AC because I can break that down into its two smaller segments. So that's what I did for AC and for BD in step 3. I said AC is the sum of its two parts, which is AB and BC, and that BD is the sum of its two parts, which is BC and CD. And that's the segment addition postulate. And then I noticed that this AC here is the same as that AC there. And the BD is the same as the BD there. So I did some substitution where I combined steps 2 and 3. I took out the AC and replaced it with the AB and the BC. And then on the other side of the equal sign, I took out BD and replaced it with the sum BC plus CD. So substitution, some fancy substitution there. Now we see in this algebraic equation, we see this BC on both sides of the equal sign. So if I take that out, I literally subtract BC from both sides of the equation, I'm left with AB, this small segment here, is equal to CD, the small segment there. And so I'm really close now to what I was asked to prove. And what I was asked to prove just requires that I convert back to segment congruence instead of equality. So again, I'm going to use that definition of congruent segments to take it from an equal sign to a congruent symbol. And then of course you always have to have the segment symbol on top when you use a congruent symbol. This is a very common style of proof where we're subtracting out an overlap. We might also do the converse where we're adding in an overlap to create congruence, okay? But this is a very common style of proofs. We'll do these style with segments as well as angles, okay? So I want to make sure that we can see how we can do some substitution and then addition or subtraction to make things happen, okay? Always remembering that we're converting from congruence to equal signs.